All right, we're back recording. I got these questions printed out. And so first question, yes, these were some pretty good ones. There were a lot of ones you had to think deeply on. There were a lot of variable proportional type relationships. Two solid spheres, radius r, made of the same type of steel. Hey guys, right there. Guys, everybody full focus up here? Everybody full focus? You guys taking notes, right? You guys are taking notes? Right? Right. So when they mention what material it's made out of, they're giving you a hint as to how to think about this because they're about to blow up the sizes of these things. And then you have to think, well, if you're changing the size, what variables is that, or is that possibly not changing? Like, is the mass staying the same? Right? But the fact that they're pointing out what material it's made out of, if it's like the same density, ooh, I bet the mass is also going to scale up with the size, right? Now, how's it going to scale up? Ooh, right? Right, so they're placed in contact shown above. The magnitude of the gravitational force they exert on each other is F1. Maybe a couple asteroids floating around, they stick together, they pull together with F1. Right? When two other solid spheres, radius 3r. So we're going to scale up the radial size by a factor of 3 of the same material, same steel, placed in contact. I guess got steel asteroids. Right? What is the magnitude of the gravitational force between those? Right? So your guiding principle is Newton's universal law of gravitation, right? Probably pretty helpful for all 10 of these questions right here, right? Okay, so you're starting with this. I went ahead and wrote that down here. Now I modified it a little bit. They're the same size. So I could say the two masses are the same. Center to center distance, you could have called it d. That's okay. I call it 2r, right? Because price radius, right? So that's being squared, right? So that's like the baseline value. That's equal to F1, right? Now, how's that going to scale up with if we blow up each one by a linear factor of 3. Right? So I've got the solution written and covered up there. Right. Well, when you think about scaling, how's it going to affect each of these variables? Right. So scale up by linear factor of 3 each of these spheres. Right. I bet the center to center distance is going to very simply scale up by a factor of 3. Right. But what about the mass? Right. Because mass that occupies volume. So that should be a three-dimensional concept, right? And actually, this poster right here is perfect for this because I also have this blown up by a linear factor 3, right? You guys see a small cube versus like a big crate, right? Linear factor 3, but don't forget that's in 3 dimensions. So different properties scale up at different rates, right? Volume, mass, right? That's 3 in 3 dimensions. That's factor 27, right? 27 times, right? Right. Hopefully you guys figured that out yesterday. Okay, so 27 times the mass each one's going to be. Right. Right. So let's come back over here. The 7 times mass. I was going to say. Whoops. So one more detail. Right. The fact that we have spheres and not very nice cube boxes. Right? Does that make a difference? The fact that it's a sphere instead of a cube box. Is it still going to scale up by a 27? Yeah, it still scales up by a factor of 27. To go from a box to a sphere, you guys see I have it on the board over here. You multiply by 4/3 pi. Right? So 4/3 pi r cubed. Right? Now, even if you don't know the 4/3 pi, that's okay. What's really important is this proportional relationship. My honor students got a question that involved like an elephant growing. Right? So what if you have a small elephant and you have a tall elephant that's 3 times as tall? Guys, a 3 times as tall elephant is going to weigh approximately how many times compared to the little short elephant? 27 times, right? As long as it's like shaped the same. Right? All right. So back in here, what are you doing? Right. So I just went ahead and plugged in the proportions, which will also get straight to the answer. Right? So it's get past the 4/3 pi for a sphere, whatever. Right. Oh, you could have done that way too. Right. So I got a linear factor of 3, but to the power 3 for the mass. Right. So the new sphere is going to be 3 to the power 3 times the mass. Right. And then and there's a couple of spheres pulling on each other, so have that step twice. Right? Then out here, the center to center distance also scales it by a factor of 3, so it's 3 times the original 2r. That's all being squared. Right? Now I can pull those factors of 3 out in front, and I have 6 of those on top. Right, 3 there, 3 there. That's 3 to the 6, and then 2 on the bottom because 3 squared on the bottom. Pull that out in front. Right, and everything left over is the baseline F1. Right, right there. Right. All right. So 3 to 6 over 3 to the 2. Is that like 3 to the 4? Hey guys, what is 3 to the 4? See, 3 times 3 is 9, times 3 is 27, times 3 is 81. 81. Okay, so 81 times the force is the answer. 0.81. Okay. Okay, guys, got that? That's probably the fastest way you can solve that one. Okay. All right. Next one. satellite mass lowercase m and speed v moves in a stable circular orbit around a planet with mass capital M. Right? What is the radius of that satellite's orbit? Right, so for this one, right, is how many times have had you guys derive this in class? Say, pull out your notes. Can you derive orbital speed from scratch? Right, like I said, 1, 2, 3 steps, one by one. Right? If this was a free response question, you definitely have to write down every single step. Right, 1, 2, 3. Right. Now, if this is multiple choice, maybe you guys possibly have this memorized by now. Right, this final outcome for a circular orbit because you've used it so much. Right? So, I went ahead. Actually, I did rederive this. Right. But at some point you're gonna have maybe a orbital speed or some version of this. Right? But we want to solve for what is r, and I drew a little diagram here. Right. So remember, we're going from the center of the planet to the location of the satellite. That's what we're looking for. Right. So just algebra rearrangement and solve in terms of variables. Right. I'm getting this right here. Right. And hopefully you guys got that too. Right. You guys get there? Right, are we good? All right. Ready for number 3? Here. All right. Number 3. Ooh. Planet, mass, lowercase m, orbits a star, mass capital M, where the mass of the planet is much less than the mass of the star, which if they didn't mention that detail, you would assume that anyway, right? Side thought here. Do you guys know if you have like Pluto, and I think Pluto has a couple of moons. One of them, I think his name is Charon, right? Pluto's biggest moon is so large in comparison to Pluto. They actually orbit about a point, I think it's called the barycenter, that's actually outside Pluto, right? So they kind of orbit about this point, kind of, right? Now, what about our own moon compared to Earth, right? Well, if you look at like Earth versus our own moon, the barycenter is not exactly the center of Earth, but it's not too far off. So does Earth wobble a little bit because the moon's going around? Yeah, a little bit, but basically not, right? Anyway, they're just saying that here. So over explanation there. The orbit is circular, radius r, time period is capital T, right? True statements include. So they list 3 statements, and you got to figure out which ones are true statements. So go through one by one. First statement: the orbital speed is 2 pi r divided by the time period. Is that true or false? How many guys say true? True. Yeah, right? Because isn't that I think you guys have done this in some labs. Like I remember for sure, I know you guys have done this. You guys remember the lab with the Play-Doh canisters and string PVC pipe, right? You guys had to figure out what was the speed going around that top Play-Doh canister. So, well, it'd be circumference divided by time period. Hey, 2 pi r, that is circumference, right? Isn't that circumference divided by time, right? So that first statement is bing, true, right? Because there it is spelled out, right? Next statement: the gravitational force equals gmm over r squared. Oh, is that just Newton's law of gravitation? Bing, true. Third statement: if the orbital radius r were greater, time period would also be greater, right? There's a few perspectives you can have on this. One is that you could just think of an example. What if you have Earth? Like here could be Earth. Here could be International Space Station going around. Guys, how much time does it take International Space Station to make one trip around Earth? No. 90 minutes. 90 minutes about, right? But what if you back way up and go all the way to the moon, way out here? Right? Now you guys know the mass of the satellite itself has nothing to do with its how much time it takes to go around. Right? Cancels out. Right? But how much time it take the moon to go around? Like a whole month. Yeah, about 28 days you can call it. Right. So yeah. So just from that example, that answers the question, doesn't it? Right. Or you can navigate Newtonian mechanics, maybe from orbital speed. You could that could be distance over time, could plug in there and you could solve it that way, right? Which would just work you back towards Kepler's third law. Here's Kepler's third law, right? Which you could derive from Newtonian mechanics, and actually you can do one step better. You can make this an exact equation, but Kepler said this, right? Time period squared is proportional to distance cubed. Right? Anyway, it's also true. So all those 3 statements are true. Right? So the answer is E. True. All right, you guys good there? Next, planet with half of Earth's mass and half of Earth's radius is discovered. What would an astronaut who weighs 800 newtons on Earth weigh on that planet? Okay. So a few ways you could solve this. The long way is you could get the mass of this guy and you could figure out what exactly are the properties of this planet, which would take a long time. right? Because what is the mass of this guy in kilograms? About 80 kilograms, you guys think, right? And you could do the numbers, blah, 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 right? Or you could just solve this in terms of proportions, which is what I got covered up here. I'm going to do it that way, right? So here's GMM over R squared for Earth. Comes out to, okay, 800 newtons. Weighs 800 newtons. Okay. All right, now half Earth's mass, half Earth's radius. Okay. Now some side thoughts on that. What if they just said, let me focus on this detail, half of Earth's radius, right? What if, I'm going to change the premise a little bit. What if it was the same material, like made out of same Earth dirt, blah, blah, but it was just half of Earth's radius? What would you expect the mass of that planet to be? Okay, guys, half of Earth's radius, it's going to weigh less, right? Or have less mass. 3 dimensions, 3-dimensional. Oh, who's going to get this? What did somebody say? 8? Yeah, 1/8, right? Because it goes back to the scaling poster, right? I'm going to say half of Earth's radius, so that's like takes this base value, right? To the power of 3, because 3-dimensional constant mass occupies volume, right? 1/2 to the power of 3. It should have 1/8 of the mass of Earth, all else equal, right? But they're not saying it. They're saying it has half of Earth's mass. Ooh. So now who can tell me this planet here, is it made out of lead or styrofoam? Lead, right? Because it's extremely dense, right? It's I guess like 4 times as dense as it should be, right? Okay, something. Right. Anyway, that's just I thought, right? Because maybe in the back of my mind too, I'm thinking, okay, well, it is smaller, so would you weigh less, right? Like all else equal, this guy should weigh less, but maybe not in this case, right? Right. So let's solve this with proportions, right? So use this framework now for this new planet. I got let's say half the mass of Earth and half the radius of Earth there, right? And don't forget the bottom one's being squared, right? So I can take these half factors and pull it out in front. So I got a 1/2 in the numerator, and I got a 1/4 in the denominator because it's 1/2 squared. You guys see where that comes from? All right, are we good so far? Right. And then what's left behind that I didn't factor out? Hey, that represents Earth values, which is your 800 newtons, right? For that particular astronaut. Right? Guys, what is 1/2 divided by 1/4? 2. 2, right? Because take the bottom fraction, flip and multiply it. 1/2 times 4/1. Yeah, that's 2 times. Right? So we got 2 times 800 newtons. Guess what's 2 times 800 newtons? 1600 newtons, which is the answer. Okay. You guys got that in your notes? Get your notes. 1600 newtons this guy weighs on this tiny lead planet. Right, guys good with the tiny lead planet? Yeah. All right, next one. A new planet is discovered with, twice Earth's mass and twice Earth's radius. Hey, is this one exactly the opposite premise of the previous question? I think it's just the same thing, just in reverse. Well, okay, if we kind of backtrack, let me go back. Let's go back to the last one, right? Because I think we can kind of make a logical conclusion from this, right? If it was half Earth's mass and half Earth's radius, and this guy ends up weighing overall twice as much, then if you just go the other way and you have a planet with double the mass, double the radius, yeah, he should weigh half as much. You guys think? Right? Just go the other way, right? It's gonna be the same setup. I'll solve it like the same way, right? Which that's the question. So he weighs 500 newtons on Earth. What does he have to weigh on this planet? And you guys would say what? Yeah, 250 is the only one that like follows logical sense from what we just did, right? Let me show you guys the full proof on that. Right. So here's GMM over R squared for Earth values, comes out to 500 newtons, right? Right now the new planet, okay, well, twice Earth's mass, but also twice Earth's radius, right? Guys, is this planet made out of lead or styrofoam? Styrofoam we're going with, right? It's a giant puff planet, right? Because it should be like 8 times the mass, but it's not. It's only twice the mass, right? Right. So then, right, pull out 2 in the numerator, pull out 2 squared, which is 4 in the denominator, and then here's Earth values. Boom, half of 500 is 250 newtons. There you go. All right, you guys go with the giant puff planet. All right, next one. A newly discovered planet is found to have a density of 2/3 of Earth's density and twice Earth's radius. What's the gravitational field at the surface of the planet? Okay, so this is kind of like what we've been doing, but maybe it's like one step deeper, right? Do you guys see on the board I have density is mass over volume? So it's Greek letter, or here, I'll write this too for the video, right? So on the board I wrote density, that's Greek letter rho for density, is mass over volume. Therefore, you can rearrange that and get mass is equal to density times volume, right? Just to write what else I got on the board, so you can see this on the video at home. I said volume is proportional to r cubed, which is really all you need to solve this. Right? Now, if you want to get a bit more deeper, you could say volume of a sphere. This plane is probably pretty close to a sphere, and call it 4/3 pi r cubed. But again, just like for the ones we've been doing all along, if you didn't know the 4/3 pi to turn into a sphere, that's okay. You can still get the correct answer just from this proportional relationship. Okay. All right. Okay. You guys good? All right. Let's check out solution. Here, let's check out the solution. Okay. So gravity-filled surface of a planet. That's what we're being asked about. So here's Earth values. G mass Earth over radius of Earth squared comes out to. Now you could go 9.8 or 10 Newton per kilogram. Right. Okay. So this. Okay. All right. Then how about this new planet with I kind of skipped a step here, but I think you guys can put the pieces together, right? Instead of mass, it's just this density times volume. That is mass, right? Density times volume, right? So I got density and volume here, right? And then I went ahead and subbed in the new values. So 2/3 density of Earth, and they said, twice Earth's radius they gave us. So okay, so I have another step. I have to take that to the power of 3 to scale to get the new volume of this planet. So it's a factor of 2 for the radius, but in 3 dimensions for, okay? Right. Okay, see that? So yeah, maybe I could have squeezed in a couple other steps between here and here. Okay. And then here's twice Earth's radius again and squared. Right? That twice Earth's radius, remember, there's competing effects. It's making the planet like more voluminous and therefore probably more massive. Right? But at the same time, whoever's standing at the surface is getting further away from the surface. So there's this competing effect. Like I said, right? Overall, it's going to make them heavier. But okay. Right. So then what we got here? Got 2/3 I'll pull out in front. Okay. So 2/3 from this density. I got 2 to the power of 3 is 8. So I pull out 8 there. And then in the denominator, 2 squared, pull that out in front 4. Now, everything that I didn't pull out, hey, we're back to Earth values. And I know what that is. I call it either 9.8 or 10 Newton per kilogram. Boom. Right. And I just multiply those numbers in. Right. So the closest answer here is about 13 Newton per kilogram. Actually, if you do 9.8, that you get really close to that. If you do 10, it's like 13.3 or something like that, right? But the answer is D. Okay. All right, guys, good with the 2/3 density planet? Good. All right. All right, next one. A spacecraft is placed in circular orbit. All right, okay, so circular orbit, I'm already thinking this. All right, so you guys got this in the back of your mind? Okay, so probably something like that we're about to be navigating. The mass is 6.4 times 10 to the 23 kilograms. Right, so is that about a tenth of Earth's mass, I think, somewhere thereabouts. The spacecraft has a height of 4.5 times 10 to the 7 meters above the planet's surface. Ooh, guys, notice that little detail right there. Are they telling you the distance to the center of the planet or the altitude? This is the altitude, isn't it? Do I have a picture for that? Oh, I do have a picture. Here's my picture right here. Right. So notice they didn't tell you the center distance to the center, which is what feeds into this equation. Right. No, they told you this altitude h. Right. Okay. What additional information to calculate the speed of the planet in orbit? Okay. So here's speed, orbital speed, square root gm on r. Right. So universal gravity constant. Let's say we know that, or you're allowed to know that. Mass of the planet. Bam. We have that right there. Remember, the mass of the satellite ends up canceling out. Oh, cancel it out. Right there and there. Goes away. Right. So we don't need that. Right. But we do need the distance to the center of the planet, which we don't quite have. Right. I mean, I guess if you had the radial size of the planet, you could add that to the altitude, and that could get it for you, right? So, right, so go through here. Right, so A is not quite true. B, yeah, B. If we knew the radius of the planet, that would be enough to do it, because we get add that to the altitude and get to the center distance. Okay. Option C, the spacecraft's mass, no, that canceled out. So no matter how massive, doesn't change the answer. Right. Okay, yes. And then D is both B and C. So the answer is just B. Okay. we're good. We're good. All right. Next one. A spaceship traveling from the Earth to the moon. Which of the following is true of the gravitational force on the ship to the two objects when the ship is equidistant from the Earth and the moon, equidistant. So I drew a diagram down here. Let's take a look. All right, got here's the Earth, here's the moon. Now equidistant means like geometrically halfway, like right in the center, right? Right. Well, let's think we kind of figure out about this before we read the answers, right? And so, where's there a greater force, to the left or to the right? To the left, right? Because Earth is more massive. Right? Is there a place you think where the gravity would cancel out? Yeah, closer to the moon, maybe about here, maybe about right. How about this? Suppose this craft is like headed on its way to the moon, and then they got the engines cut off and they're just coasting, right? Now there are two forces: the moon's pulling to the right, the Earth's pulling to the left, and that's unbalanced in the middle. Right? Which direction is this ship, or I should say this, is the ship speeding up or slowing down a little bit? It's slowing down a little bit, right? Because it's moving to the right, just coasting. The engines are cut off. Earth is pulling to the left more. Okay. All right, so let's check out these answer choices, see what makes sense. Say option A, there's no net force on the ship because it's beyond the influence of right. The fact that the moon is orbiting the Earth, there's definitely enough gravity field to matter for something. So A's not really gonna cut it. Option B, there's no net force because the force is balanced. Nope, right? Because you guys said the force might balance, but a lot closer to the moon, not this equidistant location. So B's no good. Option C, there is a net force. Ooh, so we're off to a good start. Because the force exerted by Earth is smaller than that of the moon. That's exactly wrong. Okay, so took a tumble there at the end. Option D, there is a net force. True, because force exerted by Earth is greater than that from the moon. Bing! Yeah, that followed the reasoning we were thinking about. So you guys go with D? You guys go with D? Right. And then let's check out option E just to make sure. All right. There is a net force because the ship must be accelerating toward the moon. Oh, okay. Well, we thought about that too. And you guys said, well, actually, it would be accelerating towards the Earth, right? If the engines are cut off, it's going to be, okay? Okay. Right. All right. The net force would be towards the Earth. All right. A vehicle lands on Mars and explores its surface. The average gravitational field surface of Mars is 3.7 Newton per kilogram. There should be a slash there for per, right? Hey, is that approximately a third of Earth's gravity field? Right? Do you guys think you would weigh about a third of on Mars of what you do on Earth? Right? Ooh, I bet you could like jump really high. Mars. The weight of the vehicle is defined as the gravitational force, right? What's exerted on it. Which of the following statements is true about the vehicle's weight, okay, gravitational force? So, it's like two answers, right? Let's go through one by one, see what checks out. Option A, the vehicle's weight was constant while it reached the surface of Mars. Well, I'm thinking as it's headed in towards the surface, this distance to the center is decreasing, therefore its gravitational force is increasing, which is not constant, right? Or if you want the graph version of this, right? I think I made this poster after I printed your thumbnail notes, so I don't think this one shows up in your thumbnails, but we did go through the story though, right? This is probably in your notes if you take notes, right? Here I have gravity field as a function of distance from the center. Here's the surface of the planet right here, right? You guys remember the story, like if you tunnel down at a uniform density planet, pretty much linear, right? Right. And if you take off in a rocket, got inverse square relationship, right? Well, here comes the spacecraft. It's coming this way. So its weight increases until it hits the surface. Okay, see that? Right. So A's no good. Option B, the vehicle's weight increased while it was descending to the surface of Mars. Yeah. So I just said that from either this equation point of view or this graph point of view. They both tell the same story, right? I mean, this equation is this part of this graph, right? It's the same thing. I mean, if you multiply by mass, right, this gravity field, the same shape. Right? Option C, the vehicle's weight always equals the normal force exerted when it lands. Well, okay, I mean, that's true at the surface, but when it's incoming, it increases up to that point, so not quite going to cut it. Option D, the vehicle weighs less on the surface of Mars compared to Earth. Yeah, that's where they want you to see this gravitational field, recognize, oh, that's less than 9.8 Newton per kilogram. So yeah, so B and D. You guys go with B and D? B, D? All right. Oh, next one. I think this is the last one right here. Number 10, an artificial satellite, say like International Space Station, orbits Earth at a speed of 7,800 meters per second at a height of 200 kilometers above Earth's surface. I think those are actually pretty realistic values, right? Like for low Earth orbit, right? That maybe just like the top of the atmosphere, I mean, kind of fades out. Right? The satellite experiences acceleration due to gravity of. And if you were up there like low Earth orbit type values, right? I think the gravity field, we could calculate it, but I want to say it's about 90% of what is down the surface. That's what I kind of remember from the past, right? 90%. So that'd be approximately 9 meters per second squared, right? Somewhere thereabouts, right? You could do the calculation, get exact value, right? Acceleration due to gravity, 39 meters per second squared. No, that's okay. Well, it's not going to get bigger, right? So it's the wrong way, right? I have a graph too here. So on the graph, when the low Earth orbit could be about here. Here's the surface. Here's low Earth orbit about surface, low Earth orbit, right? Okay. All right. Well, okay. Let's cut to the answer. It's got to be just a little bit less than free fall gravity at the surface. So less than 9.8 meters per second squared, right? Closer to 9. I did double check this one. Well, I checked all the answers. So yeah, I gave you guys all the correct answers. And that's what they went with too. All right. So you guys good with those? Good with those? I don't know where they're getting that number from. Well, the gravity field would be the centripetal acceleration, so, which would still be about 9 meters per second squared. I wonder if they did. Here, yeah. Let's touch around. I wonder if they treated this as the radial value. What would that be? That'd be c v squared over r. Well, let's see if they did that. That would be kind of silly to do, but v squared over 200, and then kilometers. So multiply by 1,000. All right. No, even that comes out like 300. I don't know where they got that number. Okay. All right, but you guys good with the answer there? Correct answer. All right. Okay. All right, we got about 6 minutes, so we're gonna read that FRQ and get started on that, but we'll have to finish that part on Monday.